Hello everyone. In this video, we are going to solve recurrences with a new method basically, which is master method. It's a new technique that it's a little bit simpler because it's like formulated for you. In previous lectures, as you may remember, we saw some other techniques such as like recursive trees, like we tried to analyze level by level. We tried to came up with some geometric series to find out what's going on and like to be able to put like an upper bound and lower bound. And another method was like using induction hypothesis and substitution method. So here in this one, it's a little bit like formulated for you, as I said, and it is a little bit simpler, but there are some rules. So as you see, like this equation here, basically it's the same formation of the like recursive algorithms we saw in the merge sort. For example, a was 2 here, b was 2, and the fn was some constant times n. And for this one, so as you see, it's just like familiar for you, and there should be some rules. So the first rule is basically a needs to be greater than 1. So what do I mean by this? If a is not 1 or less than 1, basically it means that you cannot do recursion. To be able to do recursion, a at least needs to be 1 because like you're going to be branching from this function over here, the root, and then you will have a branches of this element over here. So if a is 0, then you will not be able to recurse. So another condition, another rule is b needs to be greater than 1. So what does this mean actually? If b is 1, for example, then it means that t of n is equal to a times t of n plus the function, the cost. So each time when you recurse, basically some n level work here, some n level here, n level here. I just gave up the I just give the example for n. Basically, it goes and goes and goes, and it never stops. And in the end, basically, you're going to reach infinity, and which is something we don't want to deal with because like you cannot bound the infinity, right? So we would like to come up with like asymptotic bounds. So what does this mean is in order to apply master method, you need to have a greater, like a needs to be greater than or equal to 1, and b needs to be strictly greater than 1. And other conditions, a and b are need to be all 1 because, like for example, this can be 2 and 2 as in like in merge sort. It cannot be n or something like log n. So we should be able to analyze it, and they need to be constant. Otherwise, we cannot apply master method. Also, there is another condition which comes from the big O notation as well. You may remember that. So n needs to be greater than n naught, like which means that for large enough n, we are talking about here, and fn needs to be greater than 0. So the function, our function, needs to be positive. So let's analyze a little bit more. So as you remember, we did also from like the merge sort as well. The cost of the function, the root, comes here. And this a over here is represented by a number of branches. So the first branch, second branch, third branch, fourth branch, eighth branch. And each branch, we basically have the n over b, right? This one. And then we do some calculations here. But let's see the next step. Like basically, we are going to have another a branches for each side, right? 1, 2, 3, 4, a, 1, 2, 3, 4, a. So, and it goes and goes until we find the theta one in the leaves. So if you look at this one, right? So the fn, the cost here, fn, there's nothing with it. Here, as you see, we have this equation over here, this element here, but how many times? A times, right? Because like we branched a times. In the second level, it's a little bit more confusing, but it's easier to explain it. We have, since we are recursing once again, we have n over b squares, but this time we have a square branches in total. Why? Because we will be branching So we have a branches at this level, right? And then for each branch, I will be branching a times. So a times a is a square. That's why. Here we had like no branch and we end up with a branch. For each branch here, we are having a branches. So for this one, we will have a branches, two a branches, three a branches, a times a branches. That's why we will be having a square. And it will be exponential for other level as well. So as you see here, this is a to the power of 0. This is a to the power of 1, a to the power of 3. So it's just, you may see that it's going a to the power of I, fn over e to the power of I. So basically, this was level 0. This was level 1, right? Level 2, level I, and at the end, it's going to be the level height. And what is the height here? The height is log b, log base b of n. So we proved this like before. And what about number of leaves? So the number of leaves are going to be a to the power of height, because like we are branching from a, and we're branching like with the height, a to the power of height is equal to a to the power of log base b of n. And from logarithmic rules, you can take this n over here, replace with a. So it's basically the number of branches you have, n to the power of log base b of a. So if you have any problem with this one, this is like a little bit complicated to explain here, but I have another video for this one. It's called Logarithm for Recursions. So you may want to look at it. But we will be using basically some simple rules of logarithms, and this is one of them. So in the end, like we are analyzing the number of branches in the end for the leaves, how many branches we have. So let me quickly remove myself first. So per leaf, we have O1 operation, which is like, it can be represented with theta 1. And we have this many leaves, number of leaves. So in the end, you will be having the cost, the function will be theta and log base b of a. And we are assuming, again, once again, a and b are O1. So now what we are going to do is, we have, as you see here, for each level, we come up with these like costs, okay? And then we calculate that number of leaves, and like we assume that number of like each leaf is like theta 1. So we know, like as we did in the recursion trees, at each level how much we spent. So here you're going to compare the root fn to number of leaves, n to the power of log b base a, base b of a. So since it's a comparison, there's like basically two outcomes, maybe three outcomes, right? Like, for example, the first outcome is leaves are going to dominate polynomially. Let's say they're going to dominate polynomially. And all levels are same, but they could not be exactly same, but like same-ish, which also means that nothing is dominating polynomially, basically. So if I say n, 2n, 3n, 4n, basically these are like, we assume that they are same. And if it is like something with log n, 1 log n, 2 log n, it's still like same. We will assume that it's same. So another condition is like root dominates polynomial. It's written polynomially here, basically like the same thing. So the one and the third, the first one and the third one is vice versa, be like reverse. And this one over here, let's analyze the cost now. So if the root dominates polynomially, t of n, we are saying, is going to be theta of fn, the function. And which makes sense from recursion trees, right? We were saying the root if the root dominates, the root is the maximum one in the levels, and you can basically use it for upper bounds in recursive trees. We saw this. And you can represent this one, basically. This is like number of leaves, right? Leaves. You're saying number of leaves can be a lower bound for this case, but since like root dominates polynomially, you just add up some n value here with some epsilon. Epsilon, something like really small, closer to 0, but it's greater than 0. So there's some small difference, which means that, okay, this function is going to be omega n log base b of a, number of leaves, times n to the power of epsilon, which is like negligible. But in the end, you can write your function like this one. So for the second level, the second case, so the leaves, the example here, n to the power of 3, n cubed, and the fn to the power of n cubed. Basically, nothing dominates polynomially here. All levels look like same, and what you're going to do is getting f of n times log n of theta notation. For this one, if the leaves dominating, this is basically like vice versa. So if leaves dominating, basically you are saying fn must be like something closer to the lower bound, right? You can represent with omega notation, and it's close to the lower bound, and times n to the power of epsilon again, which is like very negligible. For this example, could be n squared 30n over 1.5. So the 1.5 is smaller than 2. Basically, this is still like number of leaves are dominating polynomially. So for technicality for case 3, basically, the case 3 was like leaves are dominating. So the case is basically saying that the branches that you have, or like the child, we can call this one child and this one's like parent. So the child basically needs to be some smaller than some fraction of f of n, which makes it which is like used like 99% of the time, like we will be seeing this, because like this is very negligible. Like this is not going to be 1.5, for example. So it's usually around, like, for example, for merge sort it was 0.5, right? We had like two children. So the child needs to be some fraction of parent. That's what we are talking about here. So let's see some examples. So for this divide and conquer, basically this is like merge sort we did. Like if it is like, if this is like Cn, it's going to be merge sort. Let's first step is like calculating number of leaves. So the number of leaves were n to the power of log base b of a, and log base b of a is log to the power of log base 2 of 2, which is 1, and n to the power of 1 is n. Okay, so in what condition f of n is equal to theta n? So for case 2, for example, how does it apply? If the case 2 is all levels are same, right, then you're going to end up having theta n log n. For f of n, if f of n is like something like O and D is like less than 1 here, meaning like exponential is like less than 1, which means that leaves dominate. So it's going to be the case 1. And then case 1, basically you have theta n again, because leaves are dominating. And for this one, let me remove myself again. F of n is like lower bound, like omega notation of n to the power of d, and d is greater than 1, meaning that we know that the root at least omega n, which takes more than n, so it will dominate the number of leaves. This will be at least n to the power of 1 point something, right? Because like d is 1, d is greater than 1. So in this case, it's going to be case 3. Root is going to dominate, and whatever function you have for this one, so we didn't answer it correctly yet, but it's going to be the theta notation f of f of n. Another example. For this example, same applies because n log base b of a, b is 4, a is 4, you will have n for number of leaves. And same condition applies, right? It doesn't matter how many branches you have here, because master method tells you that number of leaves are going to be n. How about this one? Because it's a little bit different. So the n log base b of a is n log 2 n log base log 2 base 4, which is like n squared. So the cost function here, the function is n, and number of leaves are n squared. So leaves dominate polynomially, we say, and the answer is theta n squared. So this is easy actually, because like it's easy to find the logarithm number of leaves and doing the analysis basically. But for substitution method, for example, you were just like giving values and proving for like induction for the base case and the inductive steps. And for your assumption, you need to come up with an educated guess. But this is like very simple, that it just gives you the answer right away, just comparing the levels. So for this one, now, as you see, like we have n square leaf levels, and this is also n square. So the levels are roughly same. So roughly same, which means like it's going to be multiplied by f of n is multiplied by log n. For case 3, as an example, the root level is going to dominate. And if root level is going to dominate, it's basically going to be theta n cube. So there is some extension for case 2. Basically, it's not in the textbook. Like the textbook is like CRLS. The common textbook is CRLS. So the case is, so you have, okay, this is like number of leaves, n to the power of log base b of a, but we assume that it's multiplied with some logarithm. Usually, in the previous examples, k was 0. Log to the power of 0, whatever, is just like 1. So we were not seeing it. Now, let's say if k is like greater than n equal to 1. So there's like some n log n. So the result is same. Still, you are multiplying the function f of n with log n. So which means that like if, for example, my example is going to be if you have n log n in the beginning as the root, and in the end, if you have some n levels here, so I assume that this is like not dominating polynomially. It's like roughly still same, but then I would just case 2 applies, right? And then I will make that n log n times log n, which makes it n log square n. So in previous examples, we didn't have this log n here. It was the power of 0. That's why it was like 1. And you still applied case 2 because like you said, like all levels are same. And what I'm saying is in extended case 2, so you can assume that there's log n here as well. And still the applicable case is going to be the case 2 because all levels are still like roughly same. No one's dominating polynomially. So this is the case what I'm looking for here. So here, as you see, it's log n to the power of log 2, it's going to be n1. So the number of leaves are n, and the root is n times log to the power of 5n. And we have log to the power of 5n multiplying with just second. Just multiplying with another log n here, and it makes like n log to the power of 6n. So here, number of leaves are going to be log base 2 of 4, and n to the power of log base 2 of 4 is n square, number of leaves. And it's still like the root function, the cost is n square log n. So nothing is dominating polynomially. And what I'm going to do is I'm going to multiply this one with log n again, and it will be n square log square n. How about this one? Here might be a little bit confusing, but it's still the same thing. N to the power of log base 6, 1 over here. Sorry, and then we have number of leaves are 1. And here there is, you can assume that there is something n to the power of 0 here, and this is also n to the power of 0. So which means that nothing is dominating polynomially still, and log square n times log, it's basically theta log cube n. Okay, we were talking about like n to the power of 0, n to the power of 1, which is like something greater than 0. What about like minus 1 by here? What if it is like log minus 1 n? So which is like smaller than 0. Then the extended case 2 is not applicable, but there is another definition for that one. Let's fix the screen first. Okay. So extra extended case 2, which talks about like negative power of like logarithms here, and in the end you will have like, if you have like 1, negative 1 is going to be basically, if it is like n cube log n, it's going to be n cube log n. So that's another rule, but it's not really necessary for like in your studies, or like you're not going to be seeing it a lot. It's just like an extra extended case for case 2. So let's recap the cases again. So we talked about the root, the cost at the root, and we talked about the number of leaves. We calculated the number of leaves with some like trick with logarithms, and in the end we said like either leaf level can dominate, root level might dominate polynomially, or all levels are roughly same. So you analyze and you end up with either you, for case 2 for example, you multiply f of n with log n, or for other cases, if root dominates, then it means that you take like root into the theta notation, and if the leaves are dominating, you take theta notation of the number, like leaves, number of leaves here. So we briefly talked about the technicality of cases. So we said like if here root dominates, basically you're saying leaves can be like lower bounds, but from the formulation there is some negligible epsilon value, right? And then here nothing changes, so the epsilon value will be added to this one over here because of like the exponential power. And for this case 1, yes, we were leaf level dominating, so you just like decide the upper bounds should be like from the roots, basically the root cost times n to the power of epsilon. Still same thing, it's just basically the reverse. For this one you can make it also represented with big O notation. So as you see here, so you can say big O number of leaves over n to the power of epsilon, which makes it, you're saying, okay, I'm using number of leaves because they are dominating, so this could be my upper bound, but let's give some room, which is like some epsilon here, and very negligible, but you can also represent it in textbooks, you can see this as well. But the results that we used is like perfectly fine. So if you have the conditions, if the conditions are satisfying, and then you don't have any limitation to use master method, and which is like an easier way to figure out the behavior of your recurrence algorithms. Thank you so much.